Hey everyone, and welcome back to The Explainer. I'm so excited you're joining us today because we're diving into something absolutely fascinating. You know how in chemistry we're taught all these neat, fundamental rules to predict how the microscopic universe behaves? Well, today we're looking at what happens when nature just flat out refuses to be put into rigid little boxes. We're going to explore the exceptions, the anomalies, and the incredibly fluid spectrums that actually define advanced atomic structure, chemical bonding, and periodicity.
So, what really happens when the rigid rules of chemistry simply stop working? It's a great question, right? As focused learners, we love memorizing those rules because, hey, it makes things predictable. But honestly, the real magic, the absolute core of understanding advanced chemistry, happens when the elements decide to rebel. When a pattern breaks, it's actually pulling back the curtain on the deeper, hidden energetics of the atomic world. And let me tell you, understanding exactly why those rules break is the secret to truly mastering this material.
Okay, let's take a quick look at a roadmap for today. First up, the electron rule breakers. Then, we'll look at when ionic meets covalent. And we'll wrap up with period 3 chemical shifts. Let's get right into it.
Section 1. The electron rule breakers. Time to look at some subatomic anomalies.
If you've looked at advanced multiple-choice questions, you've probably noticed they absolutely love to test transition metals and unique D-block anomalies. Honestly, these elements are kind of the troublemakers of the periodic table, and getting a handle on their quirks is completely non-negotiable if you want to predict their behavior.
Let's look at a prime suspect here, chromium. You'd normally expect its valence configuration to end in 4s2, 3d4, right? But nope, chromium actually goes with argon, 3d5, 4s1. Why on earth does it do that? Well, it turns out chromium strongly prefers a half-filled 3D subshell because it gives it enhanced electronic stability. It literally shifts an electron out of the 4s orbital just to make this happen. It's bending the rules to find a more stable, energetic resting place.
And copper follows that exact same rebellious lead, but this time for fully filled stability. Also, when these metals form ions, remember that electrons are removed from the 4s subshell first. We actually see similar energetic anomalies when we look at first ionization energy across period 3. Instead of a nice steady increase like you might expect, we get these distinct dips. For example, from group 2 to 13, the electron enters a higher energy 3p orbital, making it easier to pull away. And from group 15 to 16, electrons start crowding each other, causing spin-pair repulsion in the px orbital. They're essentially pushing each other away. So you see, these aren't random errors. They're perfectly logical, energetic shifts.
Moving right along to Section 2, when ionic meets covalent. This is exactly where our clean mathematical models crash headfirst into experimental reality.
Before we complicate things too much, let's establish a solid baseline. Lattice energy is defined as the enthalpy change when exactly 1 mole of an ionic crystal lattice is synthesized entirely from its component gaseous ions under standard conditions. And because we're forming bonds here, this process releases energy.
Now, the absolutely crucial thing to grasp here is what causes the magnitude of that lattice energy to spike. It all comes down to combining a higher ionic charge with a smaller ionic radius. When you put those two together, you get an elevated charge density. Basically, the tighter and more highly charged those ions are, the stronger the resulting lattice is going to be, and the greater the energy released.
But here is where things get truly fascinating. Take a look at this discrepancy. On one hand, we have theoretical values calculated from a pure electrostatic model. That model just imagines ions as perfect, undeformable little spheres. But then we look at the experimental Born-Haber cycle values, which represent actual real-world measurements, and they often just don't match. The real-world values are significantly higher.
Listen, these discrepancies are definitely not math errors. They're actually proof. They prove the existence of covalent character hiding within an ionic bond. Let's break down the mechanics of how this works. It happens when you pair up a small, highly charged cation with a big, electron-rich anion. It's essentially a subatomic tug-of-war. The intense charge density of that little cation literally pulls and distorts the electron cloud of the larger anion. This distortion, or polarization, completely blurs the line between ionic electron swapping and covalent electron sharing. All right, on to our final stop, Section 3, Period 3, Chemical Shifts. We're going to take a little road trip across the elements of Period 3 to see how these shifting bond characters alter real-world chemical behavior.
When we look at the periodicity of oxides and chlorides, we see some massive structural shifts. We literally start with giant ionic structures all the way on the left side of the period, and we transition over to simple molecular structures on the right. And, as you'll see, this structural journey completely and totally alters how they respond chemically.
Let's look at how this builds across the period 3 chlorides when you drop them in water. Starting on the far left, good old sodium chloride dissolves nicely into a completely neutral solution. Moving one step to the right, magnesium chloride exhibits a slight acidity, and that's actually due to that polarization we just talked about. But as we keep moving right into the simple molecular covalent structures, well, things start to get pretty intense.
Silicon tetrachloride and phosphorus pentachloride definitely do not just dissolve nicely. No way. They undergo rapid, total hydrolysis in water. This violently releases dense white fumes of hydrogen chloride gas and creates strongly acidic solutions. Think about that. We literally went from plain, neutral, salty water to dense, white, acidic fumes just by sliding across the period.
And this brilliantly illustrates how the period 3 oxides follow an exact parallel trend. Over on the left side, sodium oxide and magnesium oxide are very basic. But jump to the middle right, and silicon dioxide, SiO2, behaves as a giant covalent structure. It is so tough and structurally locked in that it only reacts with hot, concentrated alkalis.
But right in the middle of all this, right at the transition point from basic to acidic and from giant ionic to simple molecular, sits the ultimate oddball, aluminum oxide, Al2O3. It's an amphoteric oxide. Because it sits perfectly at the structural turning point of the entire period, it actually dissolves in both acids and bases. It's literally the perfect chemical bridge between two completely different worlds.
Which brings us to our core takeaway for today. Are ionic and covalent bonds truly separate boxes, or are they really just the opposite ends of a very fluid spectrum? From quirky, anomalous d-block electrons to the intense tug-of-war of polarization, nature constantly shows us that everything is connected by gradients. Understanding these fluid shifts isn't just about memorizing random exceptions. It's the absolute master key to predicting chemical behavior. So think about that the next time you're staring down a rigid textbook rule. Until next time, keep questioning the boxes.